Okay, folks, good morning. Good morning to all. So we are very sorry for having this delay here in our beginning today, because we have, like I said, we're trying to get here some of the features of the presentation ready. Namely speaking, for those who are connecting remotely, we were trying to get a way to update online the Excel pages. So we're going to try to work in Excel today. And surely in the rest of the week, there's going to be a lot of independent work using Excel. But unfortunately, we had difficulties in so if you're connecting through the web link and remotely watching this class, I'm going to try and describe what we're going to do. But the most important thing is that you have access to the PDF document. I hope everybody here has downloaded the new version. It has 33 pages, is the new version. The previous version we had 27. The key difference is that this version now has completed, I wouldn't say the word complete, but we have advanced the chapter on ordinary differential equation solutions. Okay. So what we have discussed here, we have a lot of theoretical discussion, concept discussion on our previous meeting. Today we're going to resume some of that, and we're going to fill in some technical details, some technical discussions that were not discussed in yesterday. And I'll try with that to complete, and then maybe towards the end, I hope that we're going to start creating our first solution ourselves in VBA itself. Okay, and at that point, that's something we're going to have to switch to Excel. I'm going to be working on my chair and watch what I'm doing. But then I don't think it can be, this can be followed by the folks who are connected through video conference. It's okay, it's what we can do. So I'm looking here at this page number 2 of the document. I'm looking at the table of contents, right? And the things that we have not discussed was this. The concepts of stability, error, and I didn't really complete our discussion in 2.4, parts of a numerical solution. So, if you remember what we have said yesterday, a numerical solution is one way to approach solving differential equations and understanding what is a differential equation. Sometimes we're trying to solve a real-world problem, but that real-world problem doesn't come in the shape of an algebraic equation. Conservation laws, energy, mass, linear momentum, rotational momentum, they are never format of an algebraic equation. And because of that, when we're trying to solve those types of problems, create a model to solve those problems, you're going to have to handle those differential equations. And if you remember our discussion yesterday, there are 2 ways you can approach that. Sometimes the problem is simple enough that you can have an analytical solution to solve the problem. If you're lucky, there's an analytical solution. But in this case, the analytical solutions usually are connected to something simple. Simple application, simple problem. And when it's not simple, we need to come up with a numerical solution. A numerical solution has 3 parts. Okay? Anyone remembers what those 3 parts are? numerical methods. Numerical methods is the strategy for discretization. Because you give up in trying to find the answer anywhere, anytime. You give up, okay, I'm going to find it sometimes at some places. That's discretizing. And how you're going to discretize, then you have a diversity of numerical methods based on that. And there is a numerical scheme. Numerical scheme is, okay, now that I have made a decision to discretize, that ordinary differential equation, that partial differential equation, will have to be broken down in an algebraic equation. For instance, it is not the focus of today's class, but if you have made a decision to create a finite volume discretization, then say, for instance, I'm looking at the square here in this floor, and I'm thinking of a space-time grid in which each one of those squares is a location in space and time, like graphs that shows time volume. And then what I'm interested in, okay, in this boundary over time, how much flow having, how much flow is leaving my finite volume. To achieve the algebraic equation there, you start with an integral equation, not a differential. Start with an integral equation. You perform a discrete integration of that integral equation, achieve an algebraic equation, and then solve. So that's the basis of a finite volume solution, which I more often, in terms of research, I more often develop finite volume than anything. For free surface flow, for pressurized flows and conduits, that's probably the best thing for the finite volume. Now, finite difference discretization is a discretization by points. So you have selected points that will become representatives for your entire domain. The oldest, so the first numerical scheme for a finite volume was proposed by Euler. It's called Euler scheme. I'm going to see this in a minute. For the first time that a real application of numerical methods took place was with Lewis Richardson in the 19th century. It's a very interesting application. He had a classroom, that's what Professor Rowe told us when I was in my PhD. He had a classroom full of boys that knew how to make the 4 basic operations. You know, add, subtract, divide, and multiply, and this with abacus, because it's in the 19th century. So he was modeling the structural integrity of a dam, structural mechanics, not fluid mechanics. And each boy was sitting on a table with a pencil, an abacus, paper, and he would start a computation. He would receive the papers from his 2 neighbors, the information from his 2 neighbors in the back. Okay, so if they give me that, I'm going to make this calculation to pass this paper to the neighbors in the front. So the calculation would progress over space and time with people making calculations, answering papers. And it worked. But then it didn't fail. Then he tried to apply the same method to describe the climate, weather in England. His approach. So basically, you have these tables here with kids making calculation. And so on. Right? So this is the back of the classroom, this is the front of the classroom. So these guys here and here would do some calculation, but with information that he provided beforehand. Okay, this is what I know about the dam. So you do a calculation here, you do a calculation here, and then this calculation flow will go this way until this student. Then this student here, this student here, this student here, they all provided information for this student. Whereas this student here received information from the professor. And he keeps doing this. And so on. Okay? He did work well when he was doing a calculation for structural integrity of the dam. Every table, every workstation corresponds to a location on the dam. They were computing what was the stress that this dam was experiencing over time. That's our classification of science. All right. Then he had tried to solve using the same technique weather. Right? And when we're looking at weather, it's a complete set of different partial differential equations. A type of partial differential equation that we call hyperbolic has this time scale associated with the propagation of the solution. This scheme has a name. That's a numerical scheme. It has a name. You are advancing over time, but you're centering information over space. So this is for time, centered space. Scheme. For reasons that he could not understand, he would start the calculation. He would provide information on, say, weather at the borders of the region he was interested in. And the students were not making any mistakes in their calculations. But over time, as this was progressing, the numbers would go up, overflow. Not overflow in the field, overflow on the paper. You're solving things, you start dividing by smaller and smaller numbers, and things was basically running out of control. What do we call that? It's both. So you have a sequence of repetitions that you have a small error in the calculation, and this error is amplified. It's amplified to the point that the calculation becomes unconditionally unstable. And this is called stability issues through repetition. So we don't have time in this material to go over a technique, but I would like to write down the technique to you. It's called von Neumann linear stability analysis. It's not easy, not terribly hard. Use complex calculus, calculus with complex numbers, but you can demonstrate with von Neumann linear instability analysis if a numerical scheme will be unstable for a certain set of equations. So you see, it's interesting. So just to make sure you understand, you have partial differential equations here, and you have numerical schemes here. The same numerical scheme can be applied to different partial differential equations. Okay? And partial differential equations can be solved in different numerical schemes. But there is a numerical scheme, the FTCS, will always fail for hyperbolic partial differential equations. It doesn't fail for parabolic partial differential equations. It does fail for hyperbolic. But then you hear some terms. So if you have worked with open channels, and if you applied some numerical schemes in the past, you probably heard something like this. Oh, Courant number. Or your Courant number cannot exceed 1 If it does exceed 1 and you have an explicit numerical scheme, it will go up. This comes from von Neumann analysis. Von Neumann analysis is the one way that you can calculate at what point this square number would fail. There are some numerical schemes that fail with 0.7, actually square root of 2 over 2. In terms of what's the limit for the stability of that numerical scheme. So all I want is to see, I'm going to talk about instability here, but I don't have time to talk about von Neumann linear instability analysis. If it ever comes across your way, more complex numerical scheme problem, and for reasons that you don't know, that thing is just failing every time. Trying and failing, trying and failing. Is your idea, you're trying to make it work, it's not working. Okay, why? This could be the diagnosis tool for you to find the solution for this. Von Neumann, by the way, for those of you who like science and history of science, was the guy who collected the brains across the United States to work under Robert Oppenheimer to make the nuclear bomb. So he was not the bomb because it was about creating nuclear reactors, enriching uranium, fast materials, and nuclear physics. But he was the guy who would just go across the United States, and it's incredible. By itself, just his contributions in mathematics would be sufficient for making him famous. But he was not doing that. He was a great organizer. Von Neumann is a nice person that we read about. Okay, so let's talk about this more fundamental concepts of instability. Okay, so let's move to this page on your document, page 15. All right, and we are going to look into this very, very simple ordinary differential equation. Probably the simplest of them all. This is a decay equation, right? So A here is a number with a negative value, right? Constant. And there is so simple that even the analytical solution is simple. That's the analytical solution for this. You typically don't need to construct a numerical model to solve such easy problem, but we're doing this just for the sake of demonstrating what instability looks like. Sometimes, and by the way, anyone recognizes what is the mathematical foundation that allows me to write what I wrote here? Well, this equation 2.15. This comes from mathematical theory. Which theory am I putting to write this down? What do you think? Not very good. Something new. Taylor series. So yes, there is a Taylor series. What Taylor series is? Taylor, this mathematician, provided a way that, okay, if I know what the function is at a given point, and I not only know what the function is, but I know what the derivatives of the functions are. And the function is continuous, the derivatives are continuous, everything is continuous. But I don't know what is the value of function in the neighbor point. I know everything about the function here, but I don't know there. How can I get the results there? So that's the whole idea of the Taylor series. It allows me to extrapolate from where I am to where I want to be based on what I know where I am. So in here, if I wanted to know what's going to be the future value of u, based on what I know about the function u now, so see n delta t, you have to understand calculations are done delta t by delta t, right? So I have n delta t means, okay, point in time, and this is the next point in time, n plus 1 delta t. So if I know what's happening in delta t, and I know the derivative of the function in this delta t, and I keep adding terms here, and I have a complete Taylor series. If I stop at this point, if I stop it right there, this will be the strategy that fourth order numerical scheme does. Fourth order uses just the first term, neglects the rest. We're going to understand what this neglect means numerically today. We're going to solve this equation, maybe not this equation, another equation today that shows the effect of this error in our solution. All right, so if I isolate the unknown term, so what is the unknown term? I don't know this. I want to find this term. And I know this. Do I know this term here? No, I do. I have it right there. If I plug this into here, right, I have a means to calculate numerically, that's fourth order, numerically, not analytically, what is the result of this function in the next time step, in the next time step. So I'm building the solution point by point, advancing in time. There are other numerical schemes that we don't build a solution point by point. We build all points at the same time. We call those implicit schemes. We're not solving implicit schemes, we're solving explicit schemes in which we tackle one solution at a time. Implicit schemes were very popular in the 60s, 70s, and 80s when you could not afford to make calculations small delta t, and you have to increase the delta t, solve a matrix solution, linear algebra, you have to be applied. But then instead of calculating so frequently, you calculate more, sparsely, but at the cost of having a linear algebra solution, a matrix over integral. We're not doing that. We're solving this explicitly. Most codes nowadays are realizing the benefits of doing things explicitly. And this would be a very simple solution, okay? And that would be, okay, that's a successful application of fourth order. But what if, that's I think the interesting part, what if I didn't know that? What if I made a mistake in the solution? So right now, I know I cannot make a mistake because it's very simple. But what if this equation was harder? And I was trying to make the fourth order solution here because it's a harder ordinary differential equation, partial differential equation, and I made a mistake in that. What this mistake would imply in terms of stability of the solution. So let's move to page 16. So what kind of mistake am I going to consider? I'm making this mistake here. So instead of adding here a multiplier a, which would be the correct one, I'm using another number, Aula. And instead of having this raised to the power of 1, I'm going to power p. Something else, something different. Could be just because we made a mistake. How is this mistake interfering with the stability of the solution? So then, there are some steps here in the derivation that you can see that I can write, and I can do this for the correct solution as well. I can write the solution at any time t in terms of the solution that I had at time 0. And I have this expression here, right? And I can apply this expression, take the limit when delta t goes to 0. And that's one thing about solutions. If you're making your discretization smaller and smaller, and your results are getting worse, what do you call them? Despair. Because technically speaking, that's what I'm trying to show here. If your solution is correct, and your delta t is getting smaller, your delta x, delta y, delta z are getting smaller. So CFD folks, you're making your mesh independent analysis, right? If your mesh independent analysis failed, what does this tell you? Go back to the drawing board with it again. Create a new mesh, refine the mesh at specific points. Is the turbulence model correct? Is the one that I should be using? Are the parameters correct? Is the boundary condition well posed? So many questions. But in this particular case, that's the interesting aspect. When I'm making my steps here in the derivation and I'm taking delta t to 0, this is the final expression that I have. That looks like the analytical solution. Only that this analytical solution here has these p's and alphas here that created by mistake. When I have, in this case here, so I'm exploring the results of this error. If I make my p less than 1, right, and as delta t goes to infinity here, this solution will approach infinity, which is a clear sign of instability. You see here, sometimes you see your model goes to infinity, your solution it blows up. It will not blow up so nice and clean like this, because that's a very simple problem. But that would be a sign that your numerical model, so the error here was in my numerical model and how the numerical model was present in the numerical scheme. Your numerical model was wrong. And then this error propagated all the way to the point where I have a numerical instability. If I choose values for p larger than 1, okay, then the solution will tend to u naught when delta t equals to 0. So there's no decay. If there's no decay, it's not that your solution go up and explode, but it was giving the wrong result. It's another type of instability, because you're expecting this to drop. Okay? But if p equals 1, then you have the solution you're expecting to have. The only thing that will create the deviation is that alpha is not the correct A that you're supposed to have. It only will give you the right solution if A is correct. So we call that type of analysis, we call that theoretical instability. But there is also a concept that we call practical instability. So most of the times, as we are seeing here in case of open channel simulations, you have instability occurring from small perturbations. So your boundary condition there has a small perturbation that could be natural, could be naturally occurring. But that perturbation will grow until a point that dominates the solution. And some cases, it has to do with a larger time step, that larger than what you should be using the current condition. Sometimes it has to do with an appropriate grid, that your grid is giving solutions that are incorrect because they're not properly discretized. I have seen this happening, this thing about the grid, particularly in swim pipe. I have been working in swim for many years, but not the traditional type of way people set up swim. I mean, I've done that too, but I've been using swim for research. And if you look at swim, if you ever worked with swim before, you have a link, you have a node, you have a link, you have a node, and so forth. There is no spatial discretization between two consecutive links, right? And when you're doing calculations like that, if the process that you're feeding the pipe is a strong moving event and you're dumping a lot of water in your drainage, swim is not going to give you the right result. And And I know that for a fact because I have experimental data that simulates the exact type of condition and shows that swimming underpredicts and sometimes really badly underpredicts what's the response of the system. Swimming is not crashing, it's just giving the wrong results. And it could be just a result of having inadequate spatial stabilization, right? Larger time steps, for instance, look at this. We're going to do this test today. So let's go back to the, forget the current condition for a second, let's go back to the equation. So this is the four-lawyer equation that we have, right? And now I'm going to make some analysis here. What if my time step delta t is larger than 1 divided by a? Okay. What does this mean in terms of the solution? Then the number that I have inside of this bracket here would be less than 0. So this solution here would be multiplied by a number that's less than 0. And then this guy here becomes negative. Then I'm going to calculate the next one. So this is going to be a negative number multiplied by a number less than 0, which becomes positive. So is this the way a decay happens? No. That is a type of instability, right? Very simple. It's easy to identify the instability because the mathematical model is simple and the numerical scheme is simple. And then you see this happen. But how many times do we see in our solutions a periodic oscillation happen? Frequently happen, right? Why does this happen? It could be initially time step, like this. So the time step is inadequate. Right? We're looking here a very simple way to demonstrate that. But if this number is even higher, if this delta t is larger than 2 divided by a, so it's not 1 divided by a, 2 divided by a, not only that this oscillates, but the magnitude amplifies over time. So you have an oscillation, and the oscillation grows. And obviously, this oscillation will grow to a point where your solution will explode. Just having something like that. Okay? So the ideas that we have about stability that we observe, they can be, I mean, for simple ordinary equations like that, they can be easily traced. You can go back to those concepts of practical instability and numerical and theoretical instability and demonstrate the occurrence of those things. Well, what I have here is a page, about a page and a half discussion on errors. Errors in numerical models. And there are three types of errors that we have to be aware of when we're making our numerical models, numerical solutions. Rounding error is one, obviously. You have numbers such as 5, such as Euler, such constants, square root of 2, that you can only put so many decimals there in your code to solve. Or sometimes the language has the constants there for you. You don't need to make an estimate of this. But oftentimes, you will not carry on so many decimals in this, and then rounding errors occur, and those rounding errors have to be managed somehow in your numerical solution. For instance, I do have a code I wrote about large stormwater tunnels. And I'm making calculations, say, in structures, sometimes dozens of structures at the same time, solving 5 or 6 nonlinear equations at each structure at all time steps. And you're trying to keep continuity equation happy, energy equation happy, everything happy, but situations can be so difficult that you have to make some compromises on the accuracy that you're going to try to achieve. For instance, your depth of your manhole, does it make sense to try to achieve a depth that's less than 0.1 millimeter, convert to less than 0.1 millimeter in manhole? Maybe not. Maybe at this point you're going to have so much effort on your calculation that will take a long time for you to converge. So you will have rounding errors that will always be somehow in your solution. But if your numerical scheme is stable, if you don't have instability issues, those rounding errors will be shaved off. They will never grow. But if you're going to have unstable numerical schemes, they propagate. They will grow up and just be dominate the solution. Okay? Second type of errors are integration errors. As we have seen, for instance, if I am applying, this is a Taylor series again. Okay. Zoom a little bit. This is a Taylor series again. And if I'm using a Ford oil scheme, it means that I have neglected this term, I have neglected this term, I have neglected all terms after that. Every time I'm making a calculation, I'm dropping off those terms. Every update in the calculation, I'm neglecting all those terms. What does this mean? Is this important? Well, it depends on the magnitude of these delta p's. Depends on the magnitude of the derivatives. If you have those derivatives larger, if you have the delta p's larger, neglecting those terms may mean a lot. So yes, your solution is not unstable. It's just error is there, it's bad. You have inaccuracies in the solution. And the third type of errors we have are local truncation errors. Okay. That have to do with the discretization, not so choice of time steps for discretization. There is a concept here in the end of consistency and convergence. It's a little too theoretical, a little too philosophical to go over with, but a lot of times people use the concept of convergence and consistency, right? What this means. Convergence is a more stringent concept. The solution has converged. Consistency is a little easier to obtain. So it starts with the concept of a function that is continuous and a numerical representation of the function that is discrete. That's what you have in your computer. The discrete representation of this function. And with operations that you do, like I'm going to multiply this function, or I'm going to divide, I'm going to make an exponent. Some operation that you're going to do with this function. So there's an operation that can be done continuously. This is an L with a dash in it, and a discrete version of this operation that you do with the discrete function. When you have consistency, it means that as H here is a symbol for discretization, it could be spatial discretization, it could be time discretization, but consistency means that as my discretization goes smaller, that the difference that I have between the operation that I did on the discrete function and the operation that I do with the continuous function will drop to zero. I'm not saying that the results are going to be the same. You see, the operation that I'm making with the functions are the difference between them increase and becomes zero. Okay. The truncation error, the local truncation error, is exactly this difference. So it has to do with discretization. I cannot ever make my discretization go to zero. It will never be zero. Because it's never zero, the difference between those two means that I have always a local flotation there. But what is the meaning of convergence? Convergence is much harder. So what convergence means is a global concept that, okay, I have the continuous function again. But I have the continuous function evaluated at the same points that I have my discrete function. So suppose I'm looking at the decay, and I'm looking at the decay at every second. 1, 7, 2. See, the continuous function, I can get it anywhere I want, every millisecond. But that's just calculated at the same points that I have the discrete function. So that's what this number here means, UH. The solution of the discrete function, the continuous function at the discrete points. And what is this? That's the representation, the discrete representation of that function on your solution. When both of those approach zero, as the discretization goes to zero, it means that my solutions converge. So when you're making your, again, this is very, I think that you're very working with CFD, you can see this, and I see that. When I'm looking at my mesh independence analysis, what I'm doing, I'm playing with age. And I'm looking at data measured in the field, data measured in a lab, or benchmark CFD result. And I'm trying to look at those two numbers, and I'm hoping that they're getting closer as the solution, as the solution becomes final. That's what convergence means. Is convergence different from mesh independence analysis? I mean, if you haven't worked with CFD, maybe it doesn't make sense in this way. But is this the same thing? Mesh independence analysis, what is the goal of the mesh independence analysis? Independence means that it doesn't depend, that your solution is not depending on the mesh, right? That I'm making my mesh finer and my solution is approaching the result. What I haven't seen about instability a minute ago. What happens if my time step goes smaller? Solution explodes because it's bad quality. The numerical method, the numerical scheme, somewhere along the way, I have a problem. So when you squeeze your mesh and your results are getting bad, okay, is that your mesh is not independent. Then you have a problem with the setup of the CFD model. I'm talking about the setup of the model because you're hoping that the numerical scheme and you're hoping that the mathematical model was correctly implemented in the tool, right? If you're using CFX or OpenFOAM, you're hoping that the community that created it made it right before releasing it for the world. Then it depends only on your mesh strategy. All right, so I wanted to go over these points. This is something that I haven't had time to complete this discussion on our previous class. So then we can all move to chapter 3. But before we do that, before we go to chapter 3, do we have any questions? No questions? Yes.
When we need to have a result in one point specifically and the second point and third point. And when we want a result between these points, we make a
Interpolation.
yes. When we do have a result, this interpolation can increase the error or the instability of the
Do we have naturally occurring discontinuity in our problems, in environmental problems, water resource problems? What are examples of naturally occurring discontinuities? You have, for instance, you have a groundwater contamination, we have a breakthrough front advancing, which is sharp, maybe depending on the characteristics of the forest medium. You have hydraulic jumps that propagate their discontinuities. You have shock waves in airflow. Like supersonic flow, we have shock wave propagating. Those are naturally occurring discontinuities. Flood waves in rivers may evolve into a more hydraulic jump, moving hydraulic jump, naturally occurring. So there are some occasions that naturally occurring discontinuities will occur with that function U. And then you're making an interpolation between points that you think are continuous, but in fact they're discontinuous. That will lead to errors.
But we don't have a way to know what is the only
Side of the other.
yes. And we just put this whole of errors in just one thing. We studied like that. We don't know how to know which part of the error, but depending on the length of the interpolation, and
We have ways to systematically run different cases and estimate the amount of error, what we call norms. L1 norm, L2 norms. You can compare your solution between different renditions of the model as you change the model parameters through these norms. And there may be time for us to go over the norms as we advance to next week, because then we're going to talk about partial differential equations. But norms is a way that we can compute. But the thing about the norm is that you need to have real data to compare. If you don't have real data, then what I like doing is, for instance, there are some CFD studies we've done in the past that we don't solve everything with CFD. That I do calculations with an independent method that's maybe even simpler, but it's not CFD. And I compare the results to see if they are looking alike. The approach is resembling, solutions are resembling each other. All right, so moving on to our chapter number 3. Okay, so what we're going to do today here is that I'm going to talk about a very simple problem like we have. There is this very good book about numerical methods in general by Stephen Chaka and Richard Canali. It's cited here in our material. I would recommend you to have access to this book, read this book. I also airplane engine. So we are going to use this example in our class today, but I made some changes on Chaka's example because he presents this only with what we call four order curves, which is shown here. I'm going to take the opportunity as well to show the run through the fourth order numerical scheme, which maybe some of you have seen this before. How we can solve the problem of an object falling and calculate terminal velocity using those different numerical schemes, fourth order and run through the fourth order. Why? Because then the second half of this chapter, and this is what I added between yesterday and today. you have 7 different problems that I'm proposing to you. If you want to do all 7, you're welcome. Do it. But you have to do at least 3. And of those 3 problems, I'm allowing you to choose one easy problem. And the easy problem could be problems 1 and 2 that I consider easier than other problems. Just for practicing, DBA, coding, things like that. You have to choose problem 7, which is a system of ordinary differential equations. You're solving a system, not 1 or 4 at the same time. And after you pick one of those, either 1, 2, and 7, and the rest one here is up to you. Select one. We have so I'm going to spend the rest of today's class, and what we want to do is just to go over one of those examples. And this means those of you who haven't coded before will be a chance for you to practice coding in VBA. Okay. Then the rest of the days that we have, so we're going to go back here, and you independently will be working on these other problems. And what I want to do here is not stay here and lecture to you, but help each one here individually in getting your code done. So if it happens that maybe, say, Thursday, you've done 3 problems here, you're not done. I mean, I made 7 just to keep you busy, right? We have this time, and again, I think that at this point, different experience in coding may lead to more or less problem solving. But the importance is to acquire the practice, to practice. We need this practice now, because when it comes next week, we're going to present you to partial differential equations, not ordinary equations. Partial differential equations, when we think about the mathematical solution itself, it's not that hard. I mean, the techniques are the same. It's just that you have to perform calculations, typically speaking, in space and in time. So we're going to be approaching this problem here in today. We're going to use this time that we have this week for practice. Okay, so that's the general gist, general goal of the idea. So I'm going to present a problem of terminal velocity. I'm going to discuss the steps that I want you to take as you're solving your problems. And I want you to do it nice. I want you to, if you want to write everything in Excel, all this, but do it nice so later in the future you can refer back to this, you explain it to yourself very carefully what you've done. Okay? So it's what we call, when we're coding, document your code. Because then you can remember this can be actually used in the future. So here, the first order decay here is something that we have seen before. Newton law of cooling. Actually, there's Newton law of cooling. Newton law of cooling is the second type of problem. The computation of gradually varied flow profiles. Those who have made multi-channel flow have seen this or are doing this in VBA. Computation of storm augmentation based on hydrographic calculations for which have flows according to one equation, outflows according to another equation, and then compute what the depth of this basin variation over time should look like. Same kind of thing that swing does, which is using VBA. Transmission main startup calculation. So if you're interested in water pipelines, and how the pipeline will start up if I have a pressure gradient in it, or stop if I have a pressure gradient, is ordinary differential equation. You can apply for that. Dissolved oxygen calculation, Stricker Phelps. We can see we've done this in the past. Maybe we've done this because it's relatively simple. We have an analytical solution for that. So maybe we have done solved this in the past. But we're going to solve that in VBA. finally, the harder problem is air water surgeon pipelines. That's one mandatory. So another step that you have to practice. All right? Any questions here? So what's the difference between ordinary differential equation and partial differential equation? One remembers?
Number of the independent variables.
Yeah, so for one variable, space, time. Normally speaking, most of the ODEs that we have there were solved for time, except the gradual curve flow equation was solved for space. Right? But when you have partial differential equation, you have multiple independent variables here, solving x, y, z, d, and so on. Those are the very different results. And one consequence of that is that it's easier for you to derive analytical solutions on ordinary differential equations, and much harder to do the same partial differential equations. Okay, so understanding the phenomenon, right? So the problems that I have posed to you, when you scroll back to the page and you see the problems, you're going to see that I have already provided you with the mathematical model, right? In here, I'm deriving the mathematical model. I'm not making. If you select one of the problems, I want you to derive the mathematical model. I want you to practice creating the mathematical model, so then you can apply the numerical model. For the problem of the following object, right? We know that if you jump from a plane, you're going to have a gravity force pulling you down back to Earth. And then it can be computed simply by multiplying mass times gravity. And I know that I'm going to have a lot of drag force as I'm accelerating downward, and this drag force increases with the square of the velocity, increases with the projected area that I have, increases with the drag coefficient. So in my analysis here, my drag coefficient, I'm assuming constant. But the drag coefficient actually depends on the Reynolds number that goes across it. Neglecting this depends on the density of the fluid. So air density, I'm assuming about, say, 1.2 kilograms per cubic meter. And that's it. That's what makes my expression for the drag force. Now, if you were in a typical first year, maybe second year physics class, and you're looking at the mechanics, forces being balanced, you calculate the terminal velocity as means, well, negative because they're going downward. So that would be the expression for the terminal velocity. It depends on mass, depends on gravity, depends on rho, C, and A. Okay? But our goal here, our interest here, is not the computation of the terminal velocity. It's computation of the growth of the velocity until we get terminal velocity. How long it takes for the terminal velocity to be achieved, right? And how fast is the velocity growing in this process? So I'm talking about a time-dependent situation. I'm not talking about something that is just final velocity at all. So if I'm doing this, then I have to go back to the original mathematical model that I need to solve, which is Newton's second law. That's the original Newton's second law. Well, the only difference here is that mass would be inside of this differential. But being this in solid mechanics, mass is not going to change. I can take the mass out because it's constant. So summation of forces in the vertical direction equals mass times dV, the acceleration. Velocity is what I want to calculate. That's the goal. So what do? Summation of forces. I have drag force pointing upward. I have gravity forces pointing downward. And this is my mathematical model. Right? That is the equation I have provided to each one of you. So when you look at your problems, use the mathematical models that are all provided. But I would like you to take an effort to arrive at those mathematical models at each one of the problems I'm proposing. So if I have this mathematical model, you're realizing here that I have V in the differential form, and I have V squared appearing right there. How do we call this type of differential equation? There's a name for equations like that. Non-linear differential equations. Because we have the variable that we're updating is not linearly related to the equation. It's actually, in this case, appearing in the square. It's not anything particularly hard because everything else is constant. Mass is constant, gravity is constant, rho is constant, C and A is constant. Everything else is constant. Because things are constant like that, we can actually achieve this expression here, which is the analytical solution. Some of our examples, some of our problems have analytical solutions. And when we have an analytical solution, we can calculate the size of the error. If you don't have an analytical solution, and if you have a real measurement, then you can calculate the size of the error. If you don't have any of those, the last thing you can do is measure the text to see if the solutions are just getting worse if I have my mesh size and expectation size not good. So what is interesting about this mathematical model? Well, I have a function that not many people use on a daily basis. I have here a hyperbolic tangent, right? Not something that you see every time. What is the value of the hyperbolic tangent when this number here gets large? And then say 5. 1. So hyperbolic function. So the way for you to think of a hyperbolic function easily when your head is this. If I plot the function tangent, just tangent, starts from minus infinity, goes to 0, and goes up to infinity, right? That's what the tangent. Cosine, sine, oscillates the tangent, starts from minus infinity, goes up, minus infinity goes up. That's how the tangent starts. So you get this tangent function rotate 90 degrees. This is how a hyperbolic tangent looks like. Okay, so the shape of hyperbolic tangent. The hyperbolic tangent from minus, this number here is really small, this is going to be minus 1. If this number here is large, it will approach 1. Can this number here be negative? No, you can't have negative time. None of the constants here are negative. So I can only start this function here from 0. What's the value of hyperbolic tangent at 0? 2. So what is the velocity that I have at time 0? 0. Just have it amount to the 0. So if time passes and this number here increases, what's the velocity of this function? That's right. Is this equal to the previous solution I had in force balance? It has to be, right? If it's not, it means our analytical solution is incorrect because it doesn't converge to the final solution we have for the velocity. So it appears that this analytical solution here really does work. Okay. I now have my mathematical model, and I have a means to compare my numerical solution. But that's the numerical solution. Numerical solutions are made of three parts. You told me, right? Method, scheme, implementation. What is the method we're going to use? For sake of simplicity, finite difference. So we're going to use finite difference for sake of simplicity. How many schemes in finite difference have you seen so far? One. Fourth order. Right? And you've seen it. You haven't made it, you just seen it. We're going to make it. But I would like to make a presentation of another numerical scheme. Okay? Have to be mindful of time. Okay, so if I have the velocity function at time 1, which means time 0 plus delta t, using Taylor series, dropping everything that has a higher differential term, I have four orders. This means this term, only everything else is dropped, and the VDT is known from the mathematical model. This is the VDT. Okay. Notice here that the n, I divided everything here. So this is my VDT. I'm plugging this in substitution to that. And this is the fourth order solution for my n. Okay. I'm going to present the Runge-Kutta method, which is the Runge-Kutta method presentation. But before I run the Runge-Kutta method, I would like to implement the fourth order. It just becomes that line presented. Let's make it. Let's open Excel now and let's create it. As we're opening Excel, there's one thing that we're going to realize. So why can't I simply create lots of lines in Excel and use my cells calculation based on previous cells to keep updating these numbers? I don't need to learn VBA to do that. You don't need. VBA in this case is kind of not necessarily the best option. Some of the solutions here are not necessarily the best option. The thing about VBA is it makes all of those calculations, all the rationale behind the code, so the user doesn't see how you've done it. It's on the back of the Excel. And one of the disadvantages of that is that sometimes when you open an Excel file, oh, this Excel file has macros. And Excel thinks there's a virus there. It's not going to allow you to do so. Yeah, it's a disadvantage because you can actually run malware code using macros. Possible. But for our case, we're doing this probably for our work group, for our own use. So we know that it's safe to do. As the problems become more and more complex, implementing this in Excel, the cells itself, not using coding behind, gets incredibly more complicated. Not that you can't do, but get changed. So then start looking at the advantages of using VBA. So you're going to do it today. It's going to sound simple. You're going to look at that. This is boring. Why am I doing this? It's wasting my time here. But bear with me. It's just a means for us to start practicing this. And as this process becomes more and more complex, you're going to see the benefits of doing this in VBA. So everybody here with me? Everybody okay? Yes. Okay. So we're going to create a very simple VBA code that will implement this. Okay, let's try to do this together. And as we're going through this, so if something happens along the way, your computer installation of Excel, I mean, just go around here. What Excel version do you have? My laptop here has Excel 365. If you have Excel 365, the same version I have. If you have Excel, say 2013, 2010, it should be the same. Essentially, it should be the same. But what I have right now is Excel 365. Okay. And that's a problem now because I don't know if what I'm going to do here that the folks that are going to be following this through the cameras are going to be able to keep up. I honestly don't know. I'll try. Let's see if it does it. Okay. Okay, the first thing I'm going to do here is to name this Excel file here, actually save as, and I have a folder. I'm going to call this object file 2. Okay, you can call it object file. It's just because I have an object file here, I'm going to name it different. And I'm not going to select this as an Excel workbook, but I'm going to do Excel macro enabled workbook. See, the extension is not XLS, but XLSM for macro. So I'm going to call it this way, object file 2, and save. And now I'm going to I'm going to start screen sharing from object file 2. And I hope that by doing this, this is going to be seen. Okay. Right. See, I have got no. I mean, I'm trying for the third time here. That's the last time I'm going to try to make a screen share here with the Excel file. If this is not working, what I'm going to do is that I'm going to post this Excel file, send this email to Professor Paulo, and ask him to broadcast this to the other folks that are remotely following us. Okay. So for some reason, this is really not connected. But okay. So what I'm going to do first is that I'm going to, you have to, even if you're going to create an Excel file that's going to make another bunch of calculation, you have to think that this is also the location where you're going to have the user input interface and the output interface. Both of things are done in Excel. So if you're creating a code, say in Delphi, Visual Basic, or Java, or anything like that, you have to worry about creating a user interface screen. You're not doing that in VBA. You can. It's possible for you to create kind of a form where you enter data in VBA. I don't think this is necessary because you can actually put the information nicely. You can create a nice interface in this Excel cells where you can pull the data. So here, that's what I'm doing. I'm going to start here with problems, parameters. So the parameters that the problem you have for us to solve. I'm going to put code. I'm going to increase the size of this font. 15. Which make a little wider. And now I'm going to begin typing down the parameters that are associated with my problem. So the first thing, for instance, is the mass of the object. So what's the object mass in kilograms? Those are the units that we're going to be using. What's the projected area of the object? That's the whole principle of the parachute, right? A parachute has a small terminal velocity because the projected area is huge. Let me see, maybe I can increase the zoom here. Right? So, what else do we need? Go to your mathematical model, right? What's the information that we need? So just look at here. I need the gravity, acceleration, which has units of meters per second squared. I need the density of the fluid. In this case, it's air, but it could be anything really. And density is expressed in kilograms per cubic meter. What else do we need? Well, simulation time. What's the simulation time that you want to carry on your calculations? Seconds. And then, that's one parameter we're going to explore here is the time step. What's the time step that you want to carry on your calculations? This is going to be a discrete calculation. So dt, time step, which means seconds. Do I need anything else? Oh, drag coefficient. Well, this is so important. Let me put this down and right here. Drag coefficient. What's the units of drag coefficient? No units. No dimension. All right, I think we got everything that we need. We can work with the assumption that our velocities will start at 0 because I'm dropping from a high point. So, but if it wasn't, I could put here the initial velocity as another parameter for a calculation. Okay. So far, nothing new here, right? Nothing new. Now we're going to begin adding something new. See, I have something in my Excel that I'm not sure if you do have. Look at here. Developer. Do you have this as well? This option. If you don't have, raise your hand. Let's see. 1, 2, 3, 4. You don't have a developer or desenvolvimento or something like that. So 5 people. If you're in Excel 365, you will enable, this will show up if you go here to Arquivo or File. Then there's Options. And then there's an option here for customized ribbon. And here in customized ribbon, there are options here for you to add things like insert, but among things would be here developer. So, did you follow that? I'll do it again. Go to File or Arquivo, go to the bottom here, Options, and there's the option here for Customize Ribbon, and among the options there should be something there for developer. All right, anyone here still have a problem in showing this? Everybody with me here then. So let's move to developer now. Okay? And if you haven't done anything with VBA before, you maybe don't have an idea of what this does. But there are two ways you can actually write VBA code. One thing is called macro. The other thing is actually a VBA code. A macro in Excel is something like, I'm going to start recording my step in step 1, 2, 3, 4, because I'm going to repeat it 100 times, and I want to record it instead of clicking this again. The macro is all macro. So that's something that people did in Excel many years ago to speed up working with the spreadsheet. Code is a different story. Code is real code. So here, one thing we're going to do is to we're going to insert well, I don't like that. Right, so let me see if it works. Okay, we're going to insert, and there are options that you can add to make your Excel code more automatic. I'm going to select this option here for a command button. Okay, let's click on this option here for command button, and let's draw a command button here. And I'm going to right-click on the command button, and I'm going to format this. And formatting this, no, not here, sorry. Command button, properties. Now you see there is this menu on the left, all the properties, color, font size, font type. So I'm going to change the property here, caption. Instead of writing command button there, I'm going to write calculation. So the property there is caption. Okay, I'm going to repeat what I just did. I'm going to delete that. And I'm going to do it again. I'm going to insert an ActiveX command button. I'm going to draw the command button wherever I want it to be. I'm going to right-click on command button and select properties. And among the properties here, I'm going to change caption from command button to something that is more descriptive. So calculation. I could have another command button there that could, for instance, delete all the user input. Okay, reset parameters. Because see, I could have like, now I have about 6 or 7 parameters, but if I have like 20 and I don't want to retype or delete, just click a button, delete everything. You could create a code that will delete everything. So you have multiple buttons there. In here, just for the initial test, I'm going to try to make calculation. All right, so you see there calculation, correct? You see here properties. What's next? Now it's time for us to write the code. How am I going to write the code? Is there any place in Excel that I can write the code? Not in Excel, but in the Visual Basic program that runs with Excel. So I'm going to right-click here, the button, and I'm going to click the option here to view code. And unfortunately, I cannot do much here with regards to the size of the font. Oh, come on. So unfortunately, the size of font here doesn't help. I may try to increase the size of the font by changing the size of the font in Windows. Let's see if I can do that. Space settings, scale 150. All right. Okay, so this is a little larger. Huh? What? Tools. Options.
And there'll be
Ah, good. No, good. Good. Let me change that. So, settings, go back to my. All right. Tools, options, editor format, maybe 14. Oh yeah. Can you guys? No, you can't.
It's 16 there.
To me, it's really strange here. Yeah. All right. So, as a general practice in codes, normally speaking, you have different blocks of text, especially when these blocks of text refer to scientific computation. There is a button here. So I have an English keyboard in my laptop. So there's this symbol here that looks like a prime. That symbol, like a prime, allows you to write a comment in Visual Basic. So it's not going to be a comment line, it's going to be a comment. So you're going to see that I'm writing here, and I'm writing here variables declaration, and when I hit enter, you see that it changed the color to green. Meaning, I'm not going to consider that. That's not part of the calculation. But I'm going to write the blocks of the code. So this is the first block, variables declaration. Second block will be user data input read. So I'm going to read the information that the user of the code is providing to my analysis. So those are the different blocks. So some codes, you have steady state calculations that you need to go first. And here I have preliminary steady calculations. Okay, so I'm just writing comments. And if you see that's going green in your screen, it means, okay, it's a comment. I'm not considering this in the analysis. The next block here would be, in this case, ODE solution. Time, marching, procedure. Okay. And lastly, you have something like, sometimes you may have output, user output present. We can make this very pretty, we can make it very nice. Right now, we're just going to make it work. Okay, so results presentation. Okay. I'm going to use this. And here you see at the bottom, end sub. What end sub means is that when you click that button, you're creating an event on Visual Basic. Visual Basic, Delphi, Visual Basic for applications. There are so many different application development packages that don't work like Fortran does. Fortran works, or Pascal works by procedure. You click on the procedure, it runs the procedure entirely. This kind of problem works that, so if the user clicks on that button, that button will develop a procedure. But then it keeps waiting for you to, what else are you going to do? Are you going to close the program? Are you going to click another button? So it's what we call event-based programming instead of procedural programming. Slightly different. At the core, you're still developing a procedure for calculation. So let's go to our first stage here. Variables declaration. So we need to, yes?
Are you sure that the camera is?
Yeah.
Because we are not seeing.
No, yeah, because the. I'm here. So, variables declaration. In the variables declaration, we need to list all the variables that we're going to use and all the types of variables that we're going to use. Okay. So, for instance, I know there is going to be a variable called G, it's called gravity. I know there's going to be a variable called A, that's going to be the projected area. I know there's going to be a variable called BP, that is the time step. And you can, if you want, you can name each one of those variables, like make comments in each one of them. And it's good practice to do that, but if I do that, there's no time, no way we can finish this graphically. So I'm skipping this. T, sim, simulation time. T is the current time in my analysis. A rho is the density of the fluid. C is the drag coefficient. What else? Mass. I'm going to use just M for mass. Anything else that we need to declare as variables? Velocity we're going to declare as a vector, as an array. Okay, and I know I'm going to declare 4 variables here that right now you don't understand why, but we're going to make use of this maybe next class. I'm going to call those variables dv1, dv2, dv3, dv4. Okay, and I think that's it. I think we have all the variables we need that are this type of variable. I'm going to call this variable here as double precision oh, yeah, I understand. If I'm declaring variables, I have to have a first word here called dim. So dim for dimension, declare those variables, all of those variables as double. Then I click enter, and it's okay. Accept. And you're noticing that the keywords in Visual Basic are painted in blue, and the variables are in black. So it's nice because it differentiates the mean. But there are some variables I also need. I need some integer variables. So I'm going to then here one variable called II, another variable called NPS. II is going to be an index. I'm going to vary from 1, 2, 3, 4, 5, just grow. NPS is going to be the number of time steps that I'm going to do. I think that's what I need. And I'm going to basically declare them as integer. And you're noticing that as you begin to type, Visual Basic for applications understand, oh, do you want to try it? Just hit enter and we'll finish the sentence for you. All right, and then there's going to be another variable that I'm going to declare. That's going to be the velocities I'm going to calculate, but those velocities are going to be vectors. And there's more accurate ways you can do that. You can actually have a dynamic allocation of vector sizes. I'm not going to do this, I'm going to do simple. Make it simple. So I'm going to make here V analytical for my analytical velocity. And I'm going to make this here a vector of, I don't know, 100,000 size vector, comma, BFE for Ford Euler calculation, 1,000 elements in this. And I'm going to calculate here a VRK form that's going to be later when I'm developing Runge-Kutta. I'm going to make a Runge-Kutta fourth order solutions to be stored in this vector. 1. So I'm talking about 100,000. And those vectors, okay, I have a vector this size, but what is the information I have in each vector? I'm going to put it as double. See, double precision is usually what we use for scientific calculation, but it requires more memory. Sometimes you're constrained by memory. You have so many variables, so large vectors, and one way to manage that is to make a compromise on the accuracy of those variables. Instead of making them double precision, making them single precision. Then the size of those vectors drop, and then you can actually store larger vectors. See, 100,000 is really small. You can have billions of elements in vectors, and then in some cases, this will blow up the memory RAM you have in your server. I know that this happens yet. Okay, variable declaration, let's keep this there. I think that's it. Now, you see, each one of the variables that we have declared, they're going to be used. They're going to be used either because the user has input for that, or because we have calculations for that. So let's learn how we pull data from the user. It's very simple. In Excel, it's very simple. So for instance, G, the variable G. Where have we stored the information for variable G? It's right here, right? It's this cell. This cell is the 5th row, 2nd column. Isn't it right? So G equals cells, open parentheses, row index 5, column index 2. That's it. Yes? Oh, yeah. All right. So that's how we read the value for G. What else do we have? So mass, area, and drag coefficient goes first. So let me do that. Mass equals cells to 2, correct? Second row, second column. Projected area equals cells 3, 2. Drag coefficient equals cells 4, 2. Okay, so I'm expecting to have a drag coefficient equal to a number. What if the user goes there and writes Vasco? The code is going to crash, right? I'm not making any attempt here to catch this kind of error. You can make a treatment on the user input there. But again, if I do that, we're spending time that we don't have. So let's just go ahead, realizing that those can only be numbers, what we enter in those cells. All right, after G, I have density, simulation time, and time step. So density is row, cells 6, 2. Simulation time, cells 7, 2. Are you noticing that I'm writing everything lowercase? Do you know I'm writing everything lowercase? Because if I have made no error in my command, Excel's corrected to capital. So it's a way for me to check if I made something wrong in typing and Excel doesn't correct it for uppercase. Okay, my sentence is wrong. If I try to run it, it will crash. So you see, it puts the space, it puts the uppercase, so it's nice. Okay, I understood what you did. Last guy here is delta t, dt, cells 8, 2. Okay, good. As far as data entry, we're done, right? Now we need to do some preliminary calculations. The first thing I would like to do is just to set the initial time, t, to 0. So if I'm going to run this calculation, I have to start at t equals 0. Second thing I'm going to do, if I'm making my calculations, I want to know that I have that many time steps on my calculation. How many time steps I have? So MTS, the number of time steps, is going to be the number tsim, simulation time, divided by dt, plus 1. But I'm going to round it. Round. See, it recognizes the function round and is giving you the hint. So you need a number now. Okay, how many numbers you need? I'm going to have the number that I need to calculate is tsim divided by dt. Okay? And I'm just going to close it because the order parameter is an optional. I can round it to that many digits. If I don't put any digit, it will round to just an integer number. Round plus 1. So it accepted the command. So MTS is the number of time steps I'm going to run. And the other thing I'm going to do is that I may have done this calculation before. So I want to ensure that my vectors with the solutions are all empty. Because if I'm going to do calculations many times, I want to ensure that I'm writing over clean results. So how am I going to do that? I'm going to make the calculation the following way. That's the first time I'm going to make a calculation with a repeating for to loop. So how it's done? For I equals 1 to 100,000. Okay, so I'm going to repeat this 100,000 times because I have 100,000 elements in my vector. And I'm going to write here loop. Okay, loop is the syntax we have in VBA. Okay, everything in between the for and the loop will be repeated. And what am I going to repeat? I'm going to do this. I'm going to write V analytical of II. I'm going to set it to 0. I'm going to write the same for VE, VFE, and VRK for. VFE of II will be set to 0. VRK for II is going to be set to 0. So I'm repeating these 100,000 times to ensure that I have no data written on my vectors. Everybody with me here so far? Okay, so I understand this is a little bit of algorithm here, right? So the class here is not about how to write a code, but this is very easy language to, very easy to understand what I'm trying to do. If you look at C++, for instance, this would be a little harder to write now. Visual Basic is easy by comparison. All right, so I have now the preliminary calculations done. Things that I need to do before start my calculations. So what I'm going to do now is this. I'm going to start the time marching procedure, meaning that I'm going to start at the first time step, second time step, third time step, until I get to NTS. So for II equals 1 to NTS. And I'm going to put here a loop at the bottom. So in this space here, I'm going to do all the calculations that I have to do for my analysis. Okay? So what's the first thing that I'm going to do? The first thing I'm going to do is to update the timestamp. So T equals T plus dt. So I'm no longer in time 0, I'm in dt time. And if I'm repeating this for the second time, 2 dt, 3 dt, 4 dt, and so forth. That's the time of my simulation. That's why I have variable t. Okay? So for this time, I need to compute the velocities. What's the first velocity I'm going to compute? The analytical velocity. So, and this is going to be pretty neat. You understand that Excel has a huge number of functions that is available in Excel. The language Visual Basic has far fewer functions, but you can actually pull a function from Excel and use here. I'll give you one example. Some languages like Pascal, to make an exponential is a pain. In Fortran, to make sometimes hyperbolic tangent, you can't. You have to write a function to make a hyperbolic function there so you can use. In here, you don't. You pull the function from Excel. So let's make the example. What is the formula for the analytical solution? So the analytical solution of II, which means the first time step, equals minus, so I'm going to open here, so this is the analytical solution, equation 3.6. So I'm going to write the analytical solution expression in here, right? So it's minus square root, so let's do that, minus 2 times, open parenthesis, 2 times n times g divided, and be careful with parentheses, right? If you want to ensure that everything is going to be divided by the parentheses, put the parentheses in the brackets. So here, open a parenthesis, and I have here rho times c times a, and close the parentheses. Okay, so I ensure that everything is being divided there. And I'm closing the parentheses again, so I can raise this to the power of 0.5, the square root. Right, so I'm going to raise this. It's over the keyboard 6 that has 0.5. Okay, so that's the first half of the analytical expression. The second half has the hyperbolic function, right? The hyperbolic tangent. So what do I do? I'm going to multiply that and write work sheet. I think that's the function dot worksheet function. With that little keyword, I open all possible functions that we have in Excel. And this is what function again? And hyperbolic. That one thing alone would save you so much time in doing the code because, again, you don't have to write the functions. Oftentimes when you have to write the code, you have to create a function for, say, a normal distribution from point 1 to point 2, calculate the area under that normal distribution. It's key. You don't have to write it. That's the power of VB. So tangent hyperbolic, I'm going to open the parentheses, and now enters the argument inside the hyperbolic. I understand, the line is getting huge, right? The line is getting huge. Okay. Breathe in and keep tight. So what's the term we have inside the hyperbolic function? Is right here, correct? Look at this. Square root rho C A G. So I'm going to open parentheses. So I can make my square root is rho times C times A times G, rho C A G, divided by 2 times m, mass. Close this. So the denominator is closed. Close again for the square root, and I'm going to raise this to the square root. And now I have to multiply this by 5. What's time? Do I have time computed? I just computed, right? T equals T plus delta T, so I have time. I can put time there. I multiply this by T. And I close the hyperbolic tangent. And if I click enter, and Excel puts the spaces for you, it means, okay, yes, I got you. I can do it. Yes?
I think there is an extra integration.
Maybe. Oh, yes, yes, there's an extra 2. Okay, it's. Yes. All right, so we have now the analytical solution built in. Why have I computed the analytical solution? Because I want to compute the error. So, what is the Ford-Euler solution? I'm going to write here B, F, E. And I'm going to, let's put some comments here. Comment on the top, analytical velocity calculation. It's a comment. Put another comment here, Ford Euler velocity calculation. And then I'm going to make VFE of II is going to be equal to what? Now we're going to look at the mathematical scheme. What has resulted from the mathematical scheme? I'm going to put it right there. So the mathematical scheme for Ford Euler is on page 23, is this equation here. The equation 3.10 is the equation that I should put for the Ford Euler calculation. So what is going to be my VFE calculation? So it starts with VFE of II minus 1, and this will create me a problem because, well, I can do that here. I can start with my II equals to 0 and set everything. So I'm making the first calculation, II equals 1, looking at VFE at 0. So it's going to be 0. Plus, so that's earlier time step velocity, dt, open a parenthesis, rho c AV squared divided by 2m. So rho times c times a times v fe II minus 1 squared divided by 2 times m minus gravity. So this is the mathematical model for Euler. It's exactly what I have in equation 3.10, but expressed with the variables that I have in Excel. Very, very much the same. Have I lost anybody here? Everybody with me? Okay. Now that I have everything calculated, and really calculation here is just 2 lines, I have to show the results. What are the results I'm going to show? I'm going to show 4 columns. Column number 1 is the time. Column number 2 is the analytical velocity. Column number 3 is going to be the Ford Euler solution. And column number 4 is going to be the error between one and the other. Okay? So, how are we going to do that? So I remember that I had a comment here for results presentation. So let me copy that here, results presentation. And now we're going to select where we're going to write those results in Excel. Go back to your Excel. This is what you have right now there, right? I can do something like this, very simple. Again, I want to make this simple. I'm going to write something like here. Results this result is fine. And the next line I'm going to write time separate. I'm going to write V analytical meters per second, V forward Euler in meters per second, and error. And what I will do is just maybe adjust the width of the columns. So I'm showing everything. Make the error a little wider. Okay, so I'm showing the results in those 4 columns. Which column is this? This is column E, means 5th, 6th, 7th, 8 columns. And I'm going to write from line number 3, 4, 5, 6. So I'm starting in line 3, and I'm going to start at columns 5, 6, 7, and 8. So you have to know where these columns are so you can write in the correct space. Go back to VBA. And what I'm going to do, I'm going to write cells, row index. So what I start where? I start at third line, right? So if I want to write in the third line, I will do this. I'm going to write 2 plus II, because II now is 1. And then when II is 2, it's going to be the next, and the next, and the next. And with 2 plus II will give me the right row. What is the column? If I'm writing time, which is I'm going to do, the column is going to be column 5. And I'm telling that cells 2 plus II 5 is going to be equal to T. So the current time is going to be written at that location. Cells 2 plus II 6. What should I write there? What should I write right there? Analytical solution, right? So it's going to be what? V analytical II. I just computed it. Cells 2 plus II 7 is going to be the fourth order. So that would be VFE II. And the last column, column 8, is going to be the error, right? So how am I going to define the error? I know the analytical solution is the correct one. So I'm going to get the analytical solution minus the VFE solution, and I'm going to divide by the analytical solution. So it's a relative error. So this is going to be cells 2 plus II 8 is going to be equal to the analytical. Well, actually, should open a parenthesis. The analytical II minus VFE II divided by V analytical II. Correct? If we have made no mistakes, that's it. How are we going to make a mistake? Try. So let's try. Before you try, save it. See this corner here? There's a save object, also save it. And that's going to save also the code you wrote for that button. And I'm going to minimize that. And I'm going back to my Excel file. Now, do you see here that we have a design mode selected here? While this is selected, if I try to click on the button, it will just select the button. It is not going to select the code. So if I want to run the code, I have to take this off. Unselect design mode. If I click here, don't do it. It's going to blow your code off because you have no numbers. So let's do numbers here. Mass of the object, 1 kilogram. Projected area of the object. Let's suppose that's I don't know. Maybe you don't like your cell phone, right? Maybe it's too heavy, 1 kilogram cell phone. Maybe it's too large, 12 centimeters by 12 centimeters. Maybe this is 0.0144 square meters. So 0.0144, that's projected area. I don't know what's the drag coefficient of a cell phone, because it should look like that. But typically speaking, cell phones have a drag coefficient of 0.5. I choose some of the airplane. So 0.5 for drag coefficient. Gravity acceleration, 9.807. Use that. Density of the fluid, let's assume air density is 1.2. Simulation time. How much time do you think it takes for the cell phone to reach 5 terminal velocity? 20 seconds? 30 seconds. Let's do 30 seconds. And now times that. Let's make, for now, let's make force times that. 1 second. Okay, so we're computing, yes. Shouldn't. Should not. Somehow inside the operational system in Windows, it converts that. It shouldn't. Hopefully not. So, okay, if I now click on calculation, okay, look without glue. Have I selected right? Oh, maybe it's next. Or maybe it's next in syntax instead of glue. Let me try. Right, so it complained about the syntax. I wrote this code, but I was using while instead of glue. Okay, let me try again. Save. Calculation. Nothing happening. Okay, so nothing is happening. Why is nothing happening? Try to understand. One thing that we can do, it's pretty nice to do this, is debug the code. If there's an error in the code, we can try to determine where the error is. So you see there is a gray bar on the side. I'm going to click here next to M. And if I do, you're going to notice that it's marked in red. Correct? If I try to run the code, yes. Right. Hit the key F8. F8, the function 8. In my laptop, for instance, I have to click Fn and F8. That will give you a line-by-line execution of the code. So I'm going to hit F8 and see Excel is running through these lines of code in calculation. Okay? So F8, F8. If I hover your mouse over here, Excel is going to tell you the numerical value that the variable has already assumed. Empty, because there is no. So if I keep going with F8, preliminary calculation. Yes? All right, so you're noticing here that I arrived now at this loop. And if I keep clicking here on the loop, it's going to take 100,000 times to run this. I don't have this time. So what I'm going to do is that I'm going to put another breakpoint here and hit F5. And it should jump to that place. So it skips that and jump to the next breakpoint. Why we have breakpoints? Because, see, the code is not working, and I'm trying to understand why it's not working. So I'm doing this. So let's keep hitting F8. So what time is right now? So time equals 1 second. The analytical solution is indicating that in 1 second, the object has reached a velocity of minus 9.6. What's the acceleration of gravity? 9.8. But it's not really getting 9.8 because of drag. So it's not really accelerating so fast because of the drag force. But it's in the range it should be. What's VFE? So VFE is minus 9. VFE is giving exactly gravity acceleration. I think I know what the problem is. Because what I should have done here is not write cells this, but I should write cells value. The value of the cell should be equal to this, not the cell itself. And that's why I don't think it's showing there the cells. So I'll stop the code, stop it here. You see the breakpoints we created? You just click on them again and they disappear. And I'm going to add it here. Instead of putting cells, I'm going to put cells, point, or dot, value. And see, Excel have put the capital there, it understood what you want to do. So I'm going to put value here, 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 and here. So now the value of the cell is going to be the numerical values that I computed. Okay, so let's see if it works now. Save it and calculation. Everybody got it? Okay, raise your hand if you have it. 1, 2, 3, 4, 5. All right, so let's go in each one of you and let's see what the problem is. Okay, let's start. So, let me ask the opposite. If it has not worked, raise your hand. 1, 2, 3, 4, 5. Here. Also, you see. Anyone else here? So, what else is not working here? Okay, let's go back. So problems where problems. Pessoal, quem não conseguiu mandar ainda? Ó, tudo bem. Eu sei que a gente está... Putz, alguém ouviu o relógio? Tá todo mundo, ninguém foi embora, né?
Não.
Tá bom, né? Pelo visto. Porra, olha só. Eu quero que vocês depois... Vamos fazer o seguinte. Eu sei que tem como fazer isso automaticamente, mas eu não quero ter que tornar isso automático. Eu quero que a gente faça um gráfico com essas 3 colunas aqui. Vamos fazer isso rapidinho. Eu vou ilustrar um problema para vocês. Bem? Está todo mundo vendo aqui, bonitinho, gráfico? Analítico e Euler. Está todo mundo vendo que em 1 segundo de passo de tempo tem uma diferença, aí tem o Ford Euler está meio que superestimando a velocidade. Né? Mas depois de algum tempo, o Ford Euler fica razoável, fica bem próximo da solução analítica. Né? Perfeito? Perfeito. Ok. O que acontece quando a gente muda o passo de tempo? Vamos fazer esse teste aqui. Olha só o que eu vou fazer. Não precisa de vocês fazerem isso não, só observa eu fazendo aqui na tela. Eu vou pegar o passo de tempo e vou fazer o passo de tempo aqui menor. Sei lá, 0,2 segundos. E aqui, olha só, o erro máximo que eu tenho, se eu marcar tudo aqui, vocês vão ver. O erro máximo que eu tenho é de 0,05, quer dizer, 5% de erro. É o máximo que eu tenho aqui. Se eu colocar 0,02 e rodar de novo, tá? Vou marcar o erro aqui. Na verdade, eu tenho que fazer o seguinte, tem que aumentar o tamanho do meu gráfico. Aqui, ó. Olha como é que fica a solução. Qual é o maior erro que eu tenho? Eu marco todas as telas. O maior erro que eu tenho é de 1%. Então, eu derrubei o meu passo de tempo em 5 vezes, de 1 para 0,2, e o meu erro caiu 5 vezes. Tá bem? O problema, você vê que é o First Order Accuracy. Speak in English. So that's a first order accuracy scheme. Dropping the time step by a factor of 5, the error has dropped by a factor of 5. Great. What happens if I increase the time step? So now I'm going to make the time step 3 seconds. Okay, let me delete everything. You can actually make this, you can delete those things in Excel automatically if you want. So make the calculation again. Look at that. You see the little going down? That's the onset, beginning of instability, not inaccuracy, instability. If I make the time step 5 seconds, look at the zigzag. If I make the time step 7 seconds, look at that. Remember that the amplitude begins to amplify. Remember what we studied in the theory about theoretical and practical instabilities. The nice, see, you look at the small partial differential equation, ordinary differential equation. This is boring. It's very easy. That this allows you to link theory to numerical modeling results. If I make the simulation longer, say 120 seconds, see how the results look like. If I drop the time step again, say to 4 seconds, I have oscillations, but they are decaying. We studied each one of those cases. It wasn't for this equation, it was for the first order decay. That's a little more complicated ordinary differential equation. So what do we have to do next? When we come tomorrow, I'm not going to present any new, no, I have to present one new thing. I'm going to present the Runge-Kutta numerical scheme. We're going to change this code here, and we're going to throw Runge-Kutta fourth order here, and we're going to calculate analytical, fourth order, Runge-Kutta, and the errors between analytical Runge-Kutta and analytical fourth order. And I want you to tell me what happens as you change the time steps, the stability, all these things as we change the numerical scheme. That's what we're going to do next. When we finish that, then we are going to start working on the problems of chapter 3. And at this point, remember, it's going to be, think of this as an assignment, right? Think about the mathematical model, write the mathematical model, and write the numerical scheme to solve that mathematical model. Okay? So that's what we're going to do, both with fourth order and with Runge-Kutta fourth order. So we're going to be pretty busy next time. I wanted to ensure that everybody here has a working model. Everybody has now. We have something that does work. And not only that does work, it has all the elements, repeating, if, for, loops, everything that you need to use in a more complex code, you have it there. Make more complex codes based on that. And so tomorrow is Wednesday, right? So Wednesday, Thursday, Friday, as many problems as you can solve from that list, do it. That's how we're going to spend the time. Practice leads to perfection. So that's how we're going to be developing this. All right, so it's almost lunchtime. Yeah. Everybody here recording the camera will go just 1 hour above the regular time. But I think it was useful, right? Because we actually got something working in the end. And tomorrow is going to be more coding. All right. Thank you.